left off with something around logic, quantifiers and fallacies. So we had talked about rules of inference. Logical equivalent is just when two statements are the same. So remember your fallacies, right? So direct reasoning and indirect reasoning or contrapositive are the two correct ways that we want to go from an inference and a statement to a conclusion. The ways that don't work, the fallacies, are if P then Q, not P, therefore not Q. Right? And that's not logically correct. So what's the problem with this one? What's an example where that shows that this doesn't work? So if P then Q, and then we're told not P, and therefore not Q. If you get 100 on the final, you'll pass the course. You didn't get 100 on the final, therefore you don't pass the course. Right? That does not logically follow, fortunately. Okay? So this is the fallacy of denying the hypothesis. Right? We say the hypothesis is false, and then we try to conclude that the conclusion is also false, and that's incorrect. So that's a fallacy. And the other fallacy is this: if you get 100 on the final, you will pass the course. You pass the course, therefore you must have gotten 100 on the final. Right? And it doesn't follow logically. So this is the fallacy of affirming the conclusion. So this is denying the hypothesis.
So are you going to have questions like which one of these is denying the hypothesis? Or are you going to have more like...
Probably not, but it's good to know, because if I ask you, is this true or not, and if so, prove it, and if not, explain why.
Oh.
Right? You should be able to say more than just it's a fallacy. Because that really just means it's not true. So yeah, it would be good to be able to say which is which. But I'm not going to be too upset if you get them confused. But you can remember which is which, because what we're doing here is we're saying the conclusion is true. Here we're saying the hypothesis is false. So that's how I remember which is which. All right, and then quantifiers. So existential quantifier and universal quantifier. So there exists and for all. And we looked at various things related to these. We can negate these, or we can negate the thing that's inside the thing that's being quantified. And sometimes it makes sense, sometimes it quite doesn't. But that's okay. We can combine these things. There exists an x such that for all y, or for all x there exists a y, and those aren't the same thing. The order is critical. But you've been using these, at least under the hood, for most of what we've been doing in this course, right? When we say P of n for all n, right, we're using a universal quantifier. So you've actually been using this machinery for a while. Oh, well, that works. All right. Equivalent quantifiers, fallacies, good. Okay, methods of proof, direct, indirect, and contradiction. All right, so you really want to think about proofs when you're getting ready for this exam, right? You're going to have to prove some things. I will remember to put an induction proof on, unlike the midterm. So how do we prove something, right? A direct proof, we start with something that we know, usually something that's given to us, and we show that there's certain things we can conclude from that thing that we know. And eventually we show that we can conclude whatever it is that we're being asked to prove. So given this condition, prove this other thing. Well, start with this condition and then apply the rules of inference and say, well, if this condition's true, then this other thing is true, and so on and so forth, and try to work it into this final form. An indirect proof, or proof by contradiction, says, okay, let's suppose that this thing we're trying to show is not true, and we work forward and eventually show that something that we know is true is actually false. We get a contradiction. Typically, what we're going to contradict is the thing that we were originally told was true, right? So, classic example. So prove that if n squared is even, then n is even. So write this as something in the language of propositional calculus. So let P be the proposition. N squared is even. Let Q be the proposition. N is even. And we want to prove, right? This feels like busy work sometimes writing this out, but it will keep you honest. Okay, when you're done, you can say, did we prove that P implies Q? And if you accidentally prove Q implies P, having written this down and writing out what these propositions are instead of keeping them in your head will help you notice that. So the way we can do this indirectly is suppose that Q is false, therefore n is odd, n equals 2k plus 1, n squared equals 4k squared plus 2k plus 1 equals 2 times something plus 1, n squared is odd, therefore not P. So maybe I should have said as a first step, suppose P is true. So if we suppose P is true, we can eventually show that P is false. That's the most basic contradiction, right? But this is really just a contrapositive. If we look at this as a direct proof, what we're proving directly is that not Q implies not P. And then by taking the contrapositive, we immediately get P implies Q. So a proof by contradiction is really just an indirect proof of the a direct proof of the contrapositive. Well, we often think of it as saying, let's contradict the conclusion and then find a contradiction. All right, so proofs. Important things. Make sure that you write out everything that needs to be written out. If you're talking about a proposition P, make sure you clearly state, let P be the proposition, and then write out what that proposition is. And try not to halfway through the proof scribble down in the corner P equals n squared is even, right? Put it in the top, right? I know it's a test, but you got an hour and 10 minutes. So some planning can help, right? Do a sketch of the proof on the side and then write it out or something. So make sure everything that needs to be written out is clearly specified. Everything that needs to be specified is clear. Make sure that you're proving the right thing, okay? If you're trying to prove P implies Q, don't prove Q implies P, or Q implies Q, or P implies P, right? Or P and Q implies Q, or something like that. And make sure that each step follows from the previous steps, and that you can go up to a stranger on the street and convince them this statement is true because these other things are true. All right. So working from what you know to what you don't know. When it's all right to start with what you don't know is like a proof by contradiction. All right, number theory. Oh, so even and odd numbers are good fodder for proof questions, right? Because we started with those, and you'll probably see some of those. Number theory. So divisibility, definition of divisibility, examples, and so on. So big thing to keep track of here. This will be worth at least 5 points on the exam. Meaning that if you forget this and you do it backwards, it'll probably cost you 5 points. So D, vertical bar N, means D divides N. Okay, it's a little counterintuitive because if we slanted that line a little, it would look like D divided by N. No, it's saying D goes into N. Okay, N's a multiple of D, D is a factor of N. It's an unfortunate notation. But when we talk about divisibility, we can say something like 3 divides 12, 4 divides 12, 5 does not divide 12. Put those on your note sheet, so remember. All right, modular arithmetic, you've been doing this in various things, in various forms, right? Modular arithmetic, we're basically working with remainders when you divide. So we fix some modulus, we're working modulo 37, and when we take an integer, we can reduce it, that modulo. So look at the remainder when you divide by 37. And we would want the remainder to be between 0 and 36. Okay, that's what the division algorithm gives us, this unique remainder between 0 and the moduli minus 1. So, and then we can do arithmetic on those congruences and end up with something that's congruent to if we had done the work on the original numbers and then reduced. And that lets us do things like modular exponentiation, right? We can keep reducing as we go, and then when we get to the end, we know our answer is correct modulo whatever we're working in. Prime numbers, you should know what primes are. Basic definition, there's an infinite number of primes, right? Prime is a number divisible by 1 in itself only. 2 is the only even prime. Open questions about primes. How many twin primes are there? Primes separated by 2, we don't know. We don't know if there's an infinite number or not. A formula for generating primes doesn't exist as far as we know, but there's lots of different ways to test primes. Greatest common divisor, Euclidean algorithm. So finding the GCD of two numbers. And this is just you can do it recursively, but it's really iterative. Right, so if you want the GCD of 707 and 21, write 707 is something times 21 plus something. And then write this as something times this plus something. And continue until you have a remainder of 0, and then the previous thing is your GCD. So practice that if you had some questions on it. So that's the Euclidean algorithm. Modular exponentiation, right? This is where we keep squaring a number. So if we want to find 2 to the 17th, or some number to the 17th, we can write that number modulo something. We can square it. We can square that to write the number to the 4th. We can square that to get the number to the 8th. We square it again to get the number to the 16th. Now we know what the number to the 1st and the number to the 16th are congruent to. We multiply those. We've got the number to the 17th. So it gets you up to big numbers much faster than just increasing by 1 in the exponent each time. It doubles the exponent. So that's modular exponentiation. Fermat's little theorem. Who remembers Fermat's little theorem? $100. Or whatever I have in my pocket. What?
Wait for me to pull on my notes.
Okay.
Oh,
Anything raised to the power of 10 is that number.
Say again?
Yeah, any number raised to the power of 10 or multiple of 10 is that number, or 1. So there's something like that.
There's no 10 in there though.
There's
so I have if P is,
exponent. Oh yeah.
if P is prime and I say P cross A, maybe, or P does not divide A,
Mm-hmm.
and then A to the power of P minus 1 is 1.
There you go. Right, so a to the p minus 1 is 1 more than a multiple of p. Except in the weak case where a is a multiple of p, because then a is congruent to 0. So when you raise it to anything, it's going to be 0. So that's Fermat's little theorem, and it's another way to do large exponentiation if you wanted to find a raised to something that's close to a multiple of p minus 1. Right, you know a to the p minus 1 is 1. A to a multiple of p minus 1 is also going to be congruent to 1. And then you just multiply by enough a's to get you up to your desired number. So that's Fermat's little theorem. And then applications, parity checking, hashes, check digits, cryptography, things like that. Conceptual questions there, if anything. I won't ask you to work through algorithms or prove things related to applications. Mathematical induction. So kind of like proofs, right? It's all about the technique, not the result. So what are the 2 steps for mathematical induction? So what?
Create a proposition.
Okay, create a proposition.
Base.
Base case, that's what I was thinking of for the first step.
And then the ignore part.
There's the ignore part. There's another part. Beyond the base case, what do you need to prove?
P of n implies like P of n plus 1.
Yes, the inductive step, P of n implies P of n plus 1.
Did you ever try to prove P of n plus 2 for some reason?
Sure.
Okay.
If you wanted to make a statement about even numbers, you could prove it for 0 and then show that Pn implies Pn plus 2.
And that'd be fine. You wouldn't have to first show
That's
P of n plus 2
totally
is
fine.
non-existent.
And you could rephrase that in the language of normal induction by rewriting your proposition to be something about n times 2, right? And now as you increase n by 1, you're really talking about even numbers in your proposition. Same thing if you want to prove something about numbers bigger than or equal to 100, right? You could start your base case at 100, or you could rewrite your proposition to be n plus 100 or something. But yeah, that's all valid. The basic idea is you've got to have a starting point, and then you're showing that wherever you are, you can go on to the next step. And if you put those together, you can prove that you can get to any step. That's all mathematical induction is saying. If there's somewhere to start and somewhere to move forward, you can move forward to any location.
Can we do a problem?
Sure. What do you want to do?
So 1 plus 3 plus 5, and it goes on to 2 minus 1 equals n squared.
Okay. So prove that the sum from 1 to 2n minus 1 of odd numbers is equal to n squared. So, and is this true? If n's 3, this is 1 plus 3 plus 5. Yeah, that looks good. All right, so there's our proposition Pn. And this is for n bigger than or equal to, I think this has to be for n bigger than or equal to 1. So P of 1 says 1 equals 1 squared. And that's true. There's a base case. So suppose, bless you. So suppose P of n is true. Then we know that this is true. That's just what P of n says. And there's an ignore section that I'm not showing here, but the ignore section, I would probably write out what P of n plus 1 says, and it would say that this thing should be equal to n plus 1 squared. And so I can turn this left-hand side of this previous statement into this left-hand side by just adding this peculiar looking quantity, 2 times the quantity n plus 1 minus 1. And I'm adding that to both sides. And then if you carry out the 2, that's 2n plus 2 minus 1, which is n squared plus 2n plus 1, which is n plus 1 squared, and that's all algebra. And now you simply have to observe that this is the left-hand side of Pn plus 1. Right? Pn plus 1 says add all the odd numbers up to 2 times n plus 1 minus 1. And this is the right-hand side of Pn plus 1, n plus 1 squared. So this is P of n plus 1. And since we just showed that this was true, P of n plus 1 is true, and so P of n implies P of n plus 1, therefore P of n for all n by mathematical induction. Good.
Yeah, so we don't have to do the ignore part. We can just do it like this.
The ignore part's for you. I'm going to ignore it. Well, I'll look at it, but
Okay.
but that's just for you. But that's if you're not sure how to, what you should be adding to both sides and
Yeah.
stuff, right? You're allowed to look at what P of n plus 1 says, and sometimes that gives you a hint. But the whole idea of the ignore is don't let me think that you've written P of n plus 1 as one of the steps of your proof, because you haven't proven that yet. And if you state that as one of these steps, then your proof falls apart, because P of n plus 1 hasn't yet been shown to follow from what you know. All right, so logically reason from what you know or assume. So recursive functions, we've been going crazy on these in 222. But in general, a recursive function is a function defined in terms of itself, but usually in terms of smaller values of itself. So f of n equals f of n minus 1 plus f of n minus 2. Right, there's a recursive definition of a function. Fn is defined in terms of smaller values, or f for smaller values of its argument. And when you do this, you usually need one or more base cases. Because if all we have is this, we can't actually ever find an actual function value. It just keeps being referred to as the value of other functions put together. So you need a base case. And these could be bigger numbers in some cases, like Ackermann's function. But we've always worked with function in terms of smaller versions.
It's kind of an interesting function.
This one?
Yeah.
You've seen this function before.
It's Fibonacci.
That's Fibonacci.
Would it have to be f of 1 and 0 should be supposed to be 1 for the Fibonacci?
Oh yeah, this
one
would be a really uninteresting function. Yeah, let's make those 1.
Okay, yeah.
Thanks. Otherwise, it's a fancy way of writing 0. That would be a horrible trick on the exam. Give me an exam where the answer to every question is 0. That would be like awful.
I think I was going insane or something.
Yeah,
It
yeah.
can't be right.
Yeah, that would-
Getting on the exam.
That would be horrible.
It's like there's some teachers that when they hand out the pencil marked quizzes, they'll do patterns on purpose.
Oh, really?
Yeah, they'll make
Like
like
bunny
that,
ears
and
or
also
something?
one and one.
Yeah, that's awful.
I hate that.
Yeah.
Bees.
All right, counting and such. This is all stuff post the midterm. So pigeonhole principle, right? N objects can fit into n bins. If you have n plus 1 objects in n bins, you're going to have at least 2 objects in 1 bin. Right, so basic principle, but we saw different ways to use that. Counting principle, product and sum rules. So break a task into subtasks. If you can do it as a succession of tasks, you can multiply the number of ways to do each task. That's the number of ways to do the original. If you can do a task as a choice of either this or that, right, then the sum of the number of ways to do this or that gives you the number of ways to do your original task. So those are 2 main ways of breaking things up into subtasks and counting how many ways we could do it. And then there's this principle of an inclusion-exclusion where well, that's just this. Right? If you have 2 sets A and B and you look at the number of elements in each and add those up, you'll generally get more than the number of elements in their union. Because in the union, we only count things that are in both sets once. Whereas this sum is counting those twice. So you have to subtract off how many double counts you had, which is just the number of things that are overlapping. And so we saw a few problems where you have students taking one course and some students taking course B, and you want to know how many students are taking either of these courses, and it's the number of students taking course A plus the number of students taking course B minus the number of students taking both. So that gives you the total number of students. Permutations and combinations. All right, permutations are ordered, combinations are unordered. So you had a homework set on this. You'll see similar questions. Going out to a restaurant and ordering combinations of food, right? So if the order of your selections is important, it's a permutation. And we saw a rule like this. And this is just the product rule written out in a more succinct form. So the number of ways to choose r things from n objects where you care about the order is n factorial over n minus r factorial. And it's basically saying there's n ways to choose the first object, there's n minus 1 ways to choose the second, and so on, down to n minus r plus 1 to choose the last object. And that turns out to be like this. But if you don't care about the order, right, product rule, when we break it into these tasks, we're implying an order. Right? How many ways can we pick the first student? How many ways can we pick the second student? How many ways can we pick the third student? And that's making it clear that choosing student ABC is different from choosing student BCA. Right? So if you don't care about the order, if you're just trying to choose, then you have to divide out by the number of ways that you can rearrange those R elements that you picked. So you get this different formula. And this is also written as this. And then this pops up in Pascal's triangle and binomial distribution and all kinds of things, most of which we don't have to worry about. All right, and then graphs we just finished. So I'm not sure we have to say anything about that. No Dijkstra's algorithm though. Not NO, KNOW. Okay, be sure you know Dijkstra's algorithm. Because you'll probably see that on the exam. And then grammars and languages, last week's subject. So the main mechanism we talked about were phrase structure grammars. So this set of symbols in your vocabulary, terminal symbols, start symbol, and a set of production rules. And using those to define what the words are over a language. We talked about finite state machines, and you've seen these in 250 if you took 250, so transitions from one state to another. And we can draw state diagrams to represent different machines. We can also use finite state machines to do recognition. So we typically have a starting state and we have a recognized state or states. And as your input comes in, you move from one state to another. And if you come to one of these recognized states, state with two circles, then at that point our input is recognized. So if we're trying to detect valid C programs or words or winning lottery numbers or whatever, right, we have to know if we're in a recognized state basically. And then Turing machines we talked about last, and right, make sure that you know how to describe a Turing machine in terms of a set of states. There are a few cases in the homework where people drew a diagram of how to go from one state to another. When we talk about a Turing machine, we really want a set of tuples, like if you're in state 0 and there's a character 1, then we want to move left and replace that with a 0 and go to state 1 and so on. Okay, so being able to write your machine as this collection of states, that's an important part of it. Dijkstra's algorithm, which was what I said I would grade on the homework, most people didn't seem to have any trouble with that, okay, and that's fair game for the final. A few things to keep in mind on Dijkstra's algorithm. Well, let me make a copy of this and then hand back the rest of the homework, so let's just talk about that. B, C, D, E, F. 2, 3, 5, 2, 5, 1, 2, 4. All right, so let's just run through Dijkstra's algorithm on this one more time. We're trying to find a path from A to F, so we're going to begin with node A. And we have these tentative distances of infinity. And node A has a distance of 0. And I'm going to write the full path, including that final node A itself. All right, so it's a two-step process, right? Find the unvisited node that's closest to A. We have written on each vertex a distance, which is the tentative distance from A. So we're going to find the closest node to A, and then we're going to visit it, and then we're going to relax nodes. Okay, the closest node to A is A, right? That's the node we visited. So we're going to relax every node that's connected to A. So this means we need to follow every edge from A and say if we can get to A with a distance of 0 and this edge has a length 2, we can get to B in a length of 0 plus 2, which is 2. And we say, is that better than the tentative distance? And if it is, then we update the distance and we record the path. So it's going to be A and then B. And here's another node connected to A, and that has a distance of 3. 0 plus 3 is 3. That's better. So this has a tentative distance of 3, and the path is AC. All right, and then we just keep iterating. So the next step is step 1, find the node that we haven't visited that's closest to A, right? Each of these shows our current tentative distance to A. And we've got 2, 3, and some infinities. 2 is the closest, so we're going to visit node B. And at this point, I would start a new diagram, right? So that it's clear that I did A first and then B. So new diagram. Visit B, and now relax everything that's connected to B. So 2 plus 5 is 7, that's better than infinity. So we can get here with a distance of 7 by going A, B, D. And we can get here with a distance of 2 plus 2 is 4 by going A, B, E. And that's all we can relax. There's only 2 unvisited nodes connected to B. So now we go back to step 1, we find a node that's closest to A and hasn't been visited yet, and that's going to be node 3. So this should be the third node you visit. And then we do a relaxation. Well, 3 plus 5 is 8, that's not better than 4, so we don't change it. Okay, our optimal distance to this node is still going A, B, E, and that's the only unvisited node connected, so we're done relaxing. Back to the first step, find the unvisited node closest to A. We've got a 4, a 7, and an infinity. This is our closest, so that's the fourth node. And then relax from there. So 4 plus 1 is 5. That's a superior solution. And the way we get there is A, B, E, and D. And 4 plus 4 is 8. That's better than infinity. So this is 8, and the way we get there is A, B, E, and then F, and we're done relaxing. Pick the node closest to A. We've got a 5 and an 8. This is the closest, and then relax. So there's only one edge we have to consider. This is an edge of length 2. 5 plus 2 is 7. That's better. This is a distance of 7, and the path is A, B, E, D, and then F. And now pick the unvisited node closest to A. That's the only one. There's nothing to relax, and we're finished. And now we know the shortest path from A to actually every node in the graph. Now if we only wanted to know the shortest path to E, we could have stopped once we visited E. But since we did F, we ended up getting the shortest path to everywhere. So make sure that you're not skipping steps, right? Even if you can see that this is not going to change anything, by visiting this, because 8 is bigger than 4, right? Make sure you do this in order, okay? It's an algorithm. I want to know that you can tell a computer how to do this. And make sure you relax everything. And after you're done relaxing, take the node with the shortest tentative distance that you haven't visited yet, visit that, and keep going. So most people were either got it completely correct or were very close, right, on the right track. And if you've still got questions about it, come and talk to me.
So after visiting E, we visit C because it's unvisited.
Correct. Because after we visit E,
We have two options, 5.
so we had, I think, a 7, an
Okay.
infinity, and a 3, right? And 3 is the closest node, so we visited 3, visited C.
Does the order in which you choose to visit your nodes matter?
Yes, it can.
You would want to visit A, B, then D, and then A, C, and then E, and then
Once you visit a node, you've locked in that distance.
Okay.
So if you visit a node too soon, you may be locking in a distance that's bigger than it needs to be. I don't know if we had an example of that in here. We might have. Well, when we got to D and it had a distance of 7, right, if we had decided we're going to visit that node next, we never would have been able to relax that 7 to a 5. Right, it's because this node was closer that we visited this, and then we relaxed along this edge and turned that 7 into a 5.
Wouldn't you eventually have gotten to that conclusion had you done A, B, D, and then A, C, E though? Because when you visited E, you'd update B.
You don't update nodes that you've already visited, though,
Oh, okay.
right? That's just part of the algorithm. So when it's visited, we're saying that's the shortest distance, or a shortest distance. And we're not going to go back and update it. Otherwise, we'd have to continually go back and reevaluate every node. And then you're kind of doing an exhaustive, right? I think you're kind of exploring the entire search space of paths at that point. So yeah, A first, and then B, and then, yeah. I think that's it. You're good to go. So, hopefully this was at least an interesting course in some parts. It's stuff that you'll encounter again, right? You'll take an entire course on automata theory, typically in your junior year, and you'll see a lot of this stuff again. But you're already using a lot of this stuff in 222, right? The whole recursion and mathematical induction and all that stuff is really underneath all this stuff we're doing with recursive functions and tree operations and things like that. So this is stuff that you're using and that you'll encounter. So I think you're all in good shape, right, exam-wise. I would just go over your homeworks, make sure that the things that we did on homeworks, particularly the questions I graded, but all of them, right? Make sure those make sense. Let me know if you have questions. I have office hours today from 12 to 2, and we have mostly open lab at 11, so we can talk about 215 in there also if you like. Otherwise, Monday, 10 a.m. will be your exam, and it'll be either Scott or me up here. Cool. Well, thank you for the class. I've definitely enjoyed it. And I will let you out 35 seconds early since it's our last day.
On stage,
Yeah.